based on these two archive preprints. And we're going back to this topic of contextuality, in particular Cochen-Specker contextuality. There will be no Pauli operators in this talk. So we've seen a bit of motivation for contextuality in previous talks. It's a bit different, but sort of the overarching question is quite similar, which is essentially this one in a sort of informal sense. Is there a way to describe quantum theory, or at least parts of quantum theory, in a classical way? And I hope that in this talk I will answer, at least to some extent, these questions. So first of all, why should you care? Why is this an interesting question to think about? What do I actually mean by classical? And this is also where the distinction between different notions of contextuality will come in. I'll try to give you a bit of a perspective of what the status of the field is, and then some new results. Okay, so in order to motivate this problem, let me give you a bit of a historical background for this question, why this has been asked. I like to think about it this way. So at the beginning of quantum theory, people were quite puzzled by this new formalism. How should it be interpreted? For instance, the Heisenberg uncertainty relation, suggesting that the theory is actually fundamentally probabilistic rather than deterministic, as it was the case in classical theories. And Bohr even raised this idea to a principle of complementarity, which is to say that actually you can't describe physics or a quantum system fully in principle. Yeah, this sort of all falls into this Einstein-Bohr debate. Einstein taking the side that this is not the final answer. There should be something more fundamental underlying it, which might well take the form of a classical theory. And one argument, maybe the most famous one along those lines, is the EPR, incompleteness argument, which probably you all know and are aware of. Then sort of the second stage, if you like, then attempts to flesh this out more precisely. How can we write down a potential theory, a classical description for quantum theory? And in fact, von Neumann addresses this in his book on quantum mechanics. He gives an argument that Bell later calls foolish, but he essentially gives an argument ruling out the existence of what people call hidden variables, so potential classical parameters that would underlie quantum theory. And that somewhat laid to rest this discussion in the foundations of quantum mechanics for 20 years or so. And then Bohm comes along and picks up ideas by de Broglie and actually writes down such a theory. So you can have a classical description for quantum theory. It just comes with some traits that you might not think of as classical. In particular, Bohm's theory is non-local, and that's actually why people hadn't picked up on these ideas by de Broglie earlier on. And then Bell becomes interested in this problem and asks whether it's necessarily so. Like, will any classical description of a quantum system be non-local? And Bell's theorem famously says yes. You cannot describe entangled states, generally speaking, using classical theory if it's supposed to be local. Yeah, that's the more famous argument, the more famous theorem that you probably all know. And then there's another theorem which tells a similar story, and that's the one that I'll be focusing on, which is the Cochen-Specker theorem, which takes a slightly different notion of classicality, namely non-contextuality, which I'll talk about more in a second, and also says that you cannot have a classical description if it's to be non-contextual. And just to finish sort of this line of the history, the experimental tests of non-locality that you're all aware of and that recently won the Nobel Prize sort of, in a sense at least, finished this chapter of looking for hidden variables for quantum theory. But then there's sort of the latest stage, if you like, and people have picked up on this problem not from a foundational perspective, but from a computational perspective. Because if you're interested in building if you're trying to build a quantum computer and you want to outperform a classical computer, then somehow you want to do something that's not classical. So the question comes back in the sense that, well, your quantum system or the subset of quantum theory that you're describing in a quantum computation should not admit a classical description in some sense. So there's sort of, like with entanglement theory, puts these notions of non-classicality and treats them as a resource for quantum computation. And arguably that's the main interest in this problem nowadays. Okay, so as I said, from this historical perspective, I want to extract what I think are two motivations for studying contextuality. One, the second one I just said, thinking about notions of non-classicality as resources for quantum computation. And then this other one, maybe there's actually some more structural insight to be gained by formalizing these notions more precisely. In the case of entanglement, I think there's a very clear case for it. Entanglement theory has vastly expanded our knowledge of quantum theory and is at the root of quantum computation, quantum information science. Non-contextuality, or the sort of quantum version, contextuality not so much, but maybe there's something more to be gained here too. Okay, so I take this to be the motivation. As I said, there's the more familiar one that Bell studies, which is local in some sense. So more precisely, the idea is that you constrain correlations between space-like separated observers. So the assumptions that you make in your hypothetical classical description of your system is, philosophically speaking, a Reichenbach's principle of common cause, and as a background assumption, relativity. To distinguish it from this notion of non-contextuality, it's first of all, it holds for single systems, so there's no notion of composite systems necessary, and therefore also no background assumption of relativity. So it holds for local observables, but another distinction I want to focus on here is that it's a notion that applies to the observable structure of the theory, not states, at least in the sense that Kochen-Specker think about it in the way that I will think about it here. So to make this more precise, at the end of the day, how non-contextuality is formalized is as conditions on a mapping from the observable structure in quantum theory, so the self-adjoint operators on a quantum system, into what would be a classical description of such operators, so the space of measurable functions in some underlying state space, phase space of your theory. Okay, what type of assumptions do we want to impose on such a classical embedding? Well, if you don't impose any constraints, then we're back to this example that I showed you earlier. You can come up with theories that do admit, well, you can come up with classical descriptions for quantum theory. If you ask too much of such an embedding, like if you ask it to be an algebra homomorphism, for instance, or even just linearity, then you can also rule out such descriptions quite quickly. That's von Neumann's argument, essentially. And I was showing you earlier the quote-unquote claim that this was a foolish argument by Bell. The reason that he says that is that this is not an operational assumption to be made, because linearity, or the full algebra structure on your quantum system, pertains to operators that you can't simultaneously measure in an experiment, so you don't have full control over. And this is sort of where the notion of non-contextuality by Cochen-Specker comes in. So the idea is to only ask the algebraic properties of your quantum system to be preserved if you can actually fully test them experimentally, which is to say that you only want the algebraic properties to hold between commuting observables. Commuting observables in quantum theory being the ones that you can simultaneously measure. And in order to explain the condition that Cochen-Specker write down, which I'll show you in a second, let me just remind you that commutativity between observables in quantum theory takes this equivalent form. So two operators, O prime or double prime, commute if and only if there exists another operator, another mother observable, if you like, with respect to which you can write the original observables as functions. So this is important because the notion of Cochen-Specker non-contextuality, the way that Cochen-Specker, the demand that Cochen-Specker make for these embeddings epsilon is that you want to map. I think it's not on the slide. Yeah, so you wanted to map epsilon here from the quantum observables to classical observables in a way that it commutes with this with the functional calculus essentially. So it commutes with it preserves the algebraic operations between commuting observables. Okay, I should probably stop here if there's any questions on just this definition. So this is the definition as Cochen-Specker write it down originally, and the notion that I will be working with. So let me give you the results then, what goes under the name of the Cochen-Specker, or sometimes Bell-Cochen-Specker theorem. So this is not Bell's original theorem, but he proved a version of this, saying that if your quantum system has dimension at least 3, then no such classical embedding exists. So no such map which preserves algebraic relations between commuting observables. And he proves it for the case of full quantum theory. So he considers all quantum observables at the same time and essentially uses Gleason's theorem to prove this. And I want to distinguish it from the Cochen-Specker theorem by noting that Cochen-Specker, for them, it suffices to consider a finite set of observables. So they construct specifically a finite set of spin 1 observables. So for a three-dimensional quantum system for which such an embedding does not exist. I want to, refer to this as the Cochen-Specker problem to characterize subsets of quantum theory that are Cochen-Specker contextual. And yeah, just to make this point. Again, this is different from Bell's theorem, obviously, because it has nothing to do with non-local correlations. He proved different theorems, and this is a different one. And yeah, just to reiterate this distinction also, this notion here is only to do with the algebraic structure. We don't talk about states at this level. Okay, let me give you a flavor for how this theorem is proven, the Cochen-Specker theorem is proven. So actually Cochen-Specker, right after writing down this constraint in the original paper, say that this is actually a very unwieldy constraint to work with, and reduce this condition a couple of steps to arrive at something simpler to work with. So what they do is they first restrict to projections as the most simple observables that you can think of. And there it's not too hard to convince yourself the existence of such a classical embedding epsilon would imply the existence of what's usually called evaluation. So a map from the rank 1 projectors into just 0, 1. So you assign every projector a value 0 or 1, such that orthogonal projectors are never assigned both the value 1 and in any maximal set of orthogonal ones, exactly 1 is assigned the value 1. So you can think of this valuation function as picking out the projector corresponding to the eigenvalue of the observable that you're measuring. And well, once you've reduced it to this, you can just look for a bunch of projectors, or if it's rank 1 projectors, then you can think of them as rays in Hilbert space that satisfy certain orthogonality relations, and for which such a map doesn't exist, and it's usually rephrased as a coloring problem. You can think of these as two colors, 0 and 1. So there's plenty of proofs that construct sets of rays which are not colorable in this sense, which is sometimes called Cochen-Specker colorable, and these type of sets are called Cochen-Specker sets. So this graph here on the side is the graph from the original paper. So this is 117 vectors or rays that are not colorable in this sense, and therefore give you a proof of, that's the original proof of the Cochen-Specker theorem. On this slide, I want somehow to give a perspective on where the field is at present. So there's many of these proofs of similar kind. There's some other ones too, and many different formalisms trying to capture the essence of contextuality or non-contextuality. So I would argue that actually right now the situation is one of not pathwork but patchwork of different formalisms. To name a few, there's this topos and sheaf theoretic approach to contextuality. There's the graph theoretic approach and hypergraph theoretic approach. So if you're working on a related subject, on the subject, then you probably know of these, and we've already heard about Speckin's contextuality and related notions too. So I want to sort of give a more recent claim by Ottfried and collaborators in a review on the subject of Cochen-Specker contextuality, that the mathematical structure of this type of non-classicality is not super well understood. There's these different formalisms, but somehow it's not really clear what exactly is the right notion, what exactly is the right framework to tackle it with. So I would argue that, yeah, what's lacking is in some sense a unified framework that allows to compare different notions that have been introduced since, so not just this original one. I think new tools in order to have any hope of getting a better structural insight, again, like maybe similar to entanglement theory, bringing a lot of insight into the structure of quantum theory. In fact, Specker in a paper essentially claiming the result that was later proved with his PhD student Simon Kochen, suggested there should be some kind of geometric argument underlying quantum theory that is responsible for contextuality. So it would be nice to have a somewhat geometric perspective. And yeah, for this motivation of using this notion of non-classicality as a resource for quantum computation, it would also be good to have quantitative to say like how much of this resource is necessary in particular tasks. So I hope to address some of these in the main part now. I'll leave you to judge how far it got. It's definitely work in progress, but I think there's something new. So let me begin by presenting you the type of formalism that I use to describe this problem that is essentially the one of the topos approach and close to the sheaf theoretic approach that I was mentioning are two approaches to the subject. The idea here is somewhat going back to these ideas by Heisenberg and Bohr, namely to not study your quantum system as like a whole, in terms of the math, not thinking of it as this like non-commutative structures of quantum operators, but to decompose it into the commuting parts, the ones that you have arguably more like better control over in relation to experiments. So what does that mean if you try to formalize it? The idea is to think of a context as a commutative subalgebra of your quantum system, and instead of thinking of the full algebra as a non-commutative algebra, just think of all of these different contexts put together. So the structure that you get from this is simply a partial order So I call it the partial order of context, which is just all commutative subalgebras taken together, and the inclusion relations are just given by inclusion of these subalgebras. So it's probably helpful to have a picture, especially if you have not seen this before. I will consider this case of a spin-1 system, so it's a three-dimensional quantum system. So in this case, the types of contexts that you get come in three types. There's the trivial context, which just contains multiples of the identity operator. Those are observables. There's the maximal layer here, where contexts contain non-degenerate observables and are generated by non-degenerate observables. And then there's a layer in between here corresponding to contexts that are generated by and contain observables that are degenerate. And you can already see, like in this three-dimensional system, these inclusion relations become quite complicated rather quickly. Okay, so to get a bit of a better handle on these, it makes sense to think of, as I was already saying, generating observables for these contexts. So the idea is simply, pick some self-adjoint operator, some observable of your choice that generates a given context, simply in the sense, namely that if you apply arbitrary functions to it, so in the spectral calculus sense, it generates the full set. Yes, then the maximal layer will be generated by non-degenerate observables, and subcontext can then be thought of as being generated by degenerating functions acting on this choice. So again, to have a picture, so just the same picture from the last slide, but now writing these contexts in this form, where I've picked some generating observables up here. Here, the subcontext, so it's a sub-algebra of these two up here, simply arises by performing some degenerating functions on this choice of observable, which are equivalent in this sense, and therefore generate a subcontext. So I write it in this form because this notion of Cochen-Specker non-contextuality had this functional relation in the definition. So it's not exactly a proof, but it doesn't take much to convince yourself that this is exactly this partial order for that reason encodes exactly this notion of non-contextuality. So the constraints imposed on a classical embedding are precisely these partial order relations, these inclusion relations between contexts. So the idea is essentially to somehow extract this notion or this structure from this partial order. Okay, so in order to do this, I will go one step further and actually pick explicit observables. As I said, I discussed the spin-1 case here, which is also the one discussed by Cochen-Specker, but this all generalizes to high-dimensional systems. So the idea is here to actually pick the observables of a particular form. So by a spin-1 observable, I will just mean any non-degenerate observable with spectral values 0, plus, minus 1. And again, they will generate, in this case, a maximal context. The important thing to note at this point is that this choice is not unique. Because if I apply some permutation on, say, the spectra of these observables, they will generate the same maximal context. Okay, so the picture redrawn again. So now I've chosen specific, these spin-1 observables up here. But yeah, these choices here are not exactly unique. And then these sub-relations, so the generating functions are essentially just the squaring operation, where now, the squaring operation will degenerate your +1 eigenspace. And yeah, the point I want you to take note of, I said it already, is that, if you think about it, the subcontext here is generated by a unique squared spin-1 observable. The ones up here are not. There's some choice which is given by the choice of permutation of the spectral values in this case. Right, and with this intuition, I want to introduce what's I think a new tool and helps to characterize this notion of Cochen-Specker non-contextuality, it turns out, which I call a context connection. So the idea is to keep track of one way to think about it is keep track of the way you can choose these maximal observables, these non-degenerate observables generating maximal context. And the way to do this is, one way to do this is to introduce a collection of maps which relate different choices of maximal observables, or more generally, actually, which relate all the observables in maximal context. So what is it? So it's a collection of bijective maps between the generating projections of your maximal context, which somehow has to preserve the partial order structure. And that's this condition here, namely that if two of these maximal contexts have a non-trivial subcontext, then this map should not permute, should not change the observables in that subcontext. the picture redrawn again. So now we have these partial order relations between contexts, and this context connection is shown in blue. So it's essentially this collection of maps up here relating between the different maximal contexts or the observables in those. And what we can do now is we can, there's another step necessary, but the idea is now to essentially concatenate these maps along maximal contexts, and in particular to concatenate them along closed loops. So this other notion that I will need is this notion of a context cycle. So it's simply a tuple of maximal contexts together with subcontexts between neighboring ones. So it would just look like something like this. So in this case, the context cycle is in white. So it's this collection of contexts and the subcontext between neighboring ones. And yeah, now I can given a context connection, I can concatenate these maps along this context cycle and see how they, if it's again, the idea is it possible to pick unique generating observables in maximal context, or is it possible to even to label the different observables in maximal context uniquely? And for that, these maps should somehow be, if you concatenate them along a loop, they should not give you inconsistencies. They should essentially be trivial. And in fact, this turns out to be the case and be fully characterizing of this notion of Cochen-Specker non-contextuality. So this is the main result I want to show you. And I phrase it here for the case of a spin-1 system, but again, it generalizes to arbitrary subsystems of quantum theory in arbitrary dimension. So the statement is that a subsystem of quantum observables is Cochen-Specker non-contextual if and only if there exists what I call, but don't get too confused by it, a flat context connection, which is such an object, such that if you concatenate these maps along any loop, along any context cycle, it's consistent. And so if you've labeled your observables starting in this maximal context C0, say, in a particular way, then that's consistent, because going in loops along context, you don't change your labeling. Right. So this, as I said, it generalizes to quantum systems of high dimension, but actually it also generalizes to this notion of a partial algebra, which, if you're not familiar with it, is fine. The point is, this is the notion that Cochen-Specker discussed in the original paper. So it justifies this claim that actually this gives a unique, gives a complete characterization of this notion. Right. So it's a characterization. Also, this framework is rather general. You can apply these tools quite generally. So I already claimed that it applies to the setting of partial algebras. Also, this. So it's different to other notions of contextuality, sometimes called marginal Cochen-Specker contextuality, but still this framework of talking about maximal context subalgebras incorporates these notions too. So this framework is capable of discussing these different structures and these different notions, and it allows therefore for a comparison of these, which I've at least undertaken for some of these different notions. And in the remainder of the talk, I want to point out a few of these because maybe surprisingly, they're inequivalent in many cases, sometimes maybe surprisingly so. So at this point, phrased as such, it's a rather formal constraint, and I didn't even apply it to a particular example because these objects, for simple systems, there's many of them. So this constraint that's the only constraint put on these is that they have to preserve subcontexts, right? And you need a bunch of contexts to even get a proof of Cochen-Specker contextuality. So there will be, the number of context connections to consider to evaluate becomes very large rather quickly. But I'll show you a reformulation of this result in a few slides, which is more easy to think of and I guess compare other results with. But the hope for the future is to make this to actually evaluate it in some examples, which I think would work by imposing more structure that would reduce the number of these connections to start with. All right, so the first thing is that Cochen-Specker contextuality is different to the existence of valuations. So I showed you that the way people proved the Cochen-Specker theorem traditionally was by finding sets of rank 1 projections or arrays for which you don't find such a coloring, such a Cochen-Specker coloring. And sure, like if you find one, then that yields a proof of the Cochen-Specker theorem, but it turns out not to be necessary. There's this example of arrays. So I've shown you this one before. So this turns out to be a set of 37 vectors in R3 or arrays, which generate 40 sets of mutually orthogonal sets of vectors. So it's essentially those vectors with squared cosine satisfy these conditions here. And this one turns out to be Kochen-Specker non-colorable. So you don't find such a well, there exists no valuation, so that yields a proof of the Kochen-Specker theorem. But then there exist these other examples which allow you to prove the Kochen-Specker theorem, but actually they do admit valuations. So rather similar example in structure is you construct the arrays or vectors with squared cosines according to these relations, and this one turns out to be Kochen-Specker colorable, but not 3 colorable. And then people have picked up on this idea and were a bit puzzled first to interpret whether this somehow deviates from the original notion of Kochen-Specker contextuality. But this actually turns out not to be the case, and it's nicely resolved, I think, with the result I showed you. So Kochen-Specker essentially proved that, if a set of rank 1 projections is not Kochen-Specker colorable, then it's contextual. But actually a stronger statement is true, and this is the reformulation I was referring to. So this condition in terms of these flat context connections turns out to be equivalent to a coloring condition on the orthogonality graph of your system, and it's in fact an if and only if statement about the system being decolorable if D is the dimension of your Hilbert space. So that at least resolves the potential confusion that there's a mismatch between the definition of Kochen-Specker contextuality as originally defined and there's more modern proofs that I showed you in the previous slide. Picking up on this example, people have then studied what's called state-independent contextuality, and in particular in this marginal approach to contextuality, where you essentially look at states, and if quantum states are classically representable. This slide is a bit busy, and it's just to introduce this notion. I just want to point out just to introduce this notion of state-independent contextuality. So it's what I want to point out is there have been partial characterizations of these structures in terms of graph colorings before, which are quite similar with this graph coloring condition I had on the previous slide, so a decolorability condition. But it was only shown in one direction, and in fact even on this level of generality, it turns out to be at odds with the previous result. So this is just if you actually have worked on this. The point is that so this condition here is only holds if you also assume that your SIC set is actually closed under complements, which people have not at least not stated in previous results down here. So arguably maybe this framework I introduced earlier is maybe more apt to study Kochen-Specker contextuality. The last point I want to make is comparing this notion of Kochen-Specker contextuality in this original sense with what's been studied more recently in the marginal approach, which essentially follows Bell's theorem and studies correlations and also tries to constrain classical correlations by using methods from convex geometry and finding something similar to Bell inequalities, which are then called non-contextuality inequalities. So here the main relation is this one. We've seen this in Martin's talk yesterday, or at least a version thereof. So now, point now is the focus is on states and not observables anymore. You asked that a quantum state, or in particular, actually every quantum state, or maybe if you consider a subset of quantum theory, then that subset of quantum states is representable classically, which just means that the expectation value that you get from quantum mechanics is reproduced in this classical form. So by taking expectation values with respect to some measure on some phase space. And just to compare those, while this is an algebraic condition that I've discussed before, this here is a condition that applies to states. And they look different a priori, and actually they turn out to be different. While in this marginal approach, as I was saying, the way you study non-contextuality is by finding these non-contextuality inequalities. Then if you find sufficiently many, then you can describe your polytope of classical states. And as I was saying, the characterization of the algebraic condition, which is different, is this one, and they're inequivalent. So I want to close with an example that shows this, and it's right. So let me first make this point. Like often it's said that contextuality is a generalization of Bell non-locality. So it's true if you think about it in this way, in this marginal sense, but it's not true if you think about it in this original sense, in this algebraic notion. Okay, I want to close with an example of a system that is Kochen-Specker non-contextual, but marginally Cochen-Specker contextual. Okay, so the example is well familiar to you. It's just a CHSH scenario. So maybe that's not so well visible. Let me try to explain. So again, the task you have if you want to prove Cochen-Specker non-contextuality is to represent the subset of observables you're interested in classically, so as functions in some underlying state space. So in the CHSH scenario, there's 4 observables. For maximal observables you care about. Alice and Bob both have one choice of spin-half measurement they can choose. So we have to represent these, and then products of their observables are just given as products of functions. The state space in this case, so this is essentially showing that you can do this. The state space here is this discrete sets of 16 states. So it's the Cartesian product of Alice and Bob's 4 ontic state spaces. If you're familiar with it, it's somewhat similar to the construction in Speckin's toy theory. So the maximum observables, if they also take plus minus 1 eigenvalues as spin 1/2 observables, you can think of spin 1/2 observables taking plus minus eigenvalues, then it's simply given by a decomposition of this state space into states where your observable takes plus and minus values. And I'm not sure it's visible clearly, but so the decomposition is somewhat going like here for this observable, and then like this for this one. Anyway, the point is you can represent these maximal observables as functions shown in these corners. The degenerate observables, which would simply be tracing out Bob's or Alice's subsystem, correspond to the corresponding context would be generated by these degenerate observables, and the fully degenerate observable, which is just the identity function, would be here in the middle. So this essentially shows the representation of your observables as functions together with the partial order of context. But yeah, not surprisingly, okay, so this says that the system is Cochen-Specker non-contextual in this algebraic sense by Cochen-Specker. But obviously it's not non-contextual in this state sense, because there exist correlations that you can't describe classically, right? I mean, there's entangled states that you can't describe in terms of a measure on this state space. And I mean, the obvious example is to look at some Bell entangled states. And one way to show it is you think of the values your quantum state, the marginals predicted by your quantum states on the respective correlations. So those would be given by these subsets here of your states, of your classical representation. And if you just sum these up, then you should somehow get these 4 contributions. Summing these 4 contributions up, you get something that's larger than 3. But so I mean, these contributions all appear once. These appear 3 times. So you should get some. If this corresponds to a classical measure, you should get something that's smaller than 3. So this is just to say that you can quickly convince yourself that Bell entangled states, more generally entangled states, and you don't even have to think about quantum theory, because this scenario allows for non-quantum states too. Yeah, not all of them will be classical. So you've violated this marginal condition of contextuality. Okay. I think this is where I want to summarize and close with some outlook. Yeah, so what I've presented to you is a new and complete characterization of this notion of Cochen-Specker non-contextuality as originally introduced, and yeah, which is algebraic in nature. I suggested that this actually yields so this sort of topos perspective, this decomposition of your quantum system into context corresponding to maximal Boolean subalgebras. I suggested there's a unified framework to discuss different notions of contextuality, in particular this one. And yeah, I've discussed some first applications. I think, some results that come out even of this formal characterization at this point. So yeah, just, for instance, just to repeat, it clarified this distinction between traditional proofs of the Cochen-Specker theorem and more modern ones. It rederives and extends and partially corrects existing conditions on coloring arguments. And I didn't actually discuss this part, but if you're familiar with this literature, there have been examples of Cochen-Specker non-contextual sets by Meyer and Kent and others. Using this condition that I showed you in terms of this, like finding a flat context connection, it's immediate that you can immediately convince yourself that these examples are non-contextual in this sense, and somewhat not surprising. So it explains, in a sense, the existence of these models. And okay, and then I want to finish with an outlook, going back to the motivation from the beginning. Yeah, one of the motivations I stated was that, hopefully maybe by having a better mathematical framework, new tools. Maybe one can regain hope at getting a better structural insight, more structural insight into quantum theory, and maybe a geometric argument for contextuality in quantum theory. So this new tool that I called it a context connection, and then you evaluate these maps along loops. So it somewhat feels or like reads similar to a notion of holonomy in differential geometry. So maybe by imposing more structure, in particular by restricting to quantum theory, that might be a direction that could be fruitful to, along this line. And similarly to use this framework to define ideally quantitative tools to study contextuality as a resource. And I don't know. In the literature on contextuality, people have been obsessed with finding minimal examples. And I guess if you actually wanted to use this, substructures of quantum theory for computation, you would be interested in having lots of them and characterizing them according to their non-classicality. So constructing them and possibly minimally constructing them using this new criteria would, you can play this game also with this new approach. Okay, I think I'll close here. And thank you for your attention.